Hi, welcome back. Today we have a question which is derive an expression for the velocity distribution and the flow rate between horizontal concentric pipe for a steady incompressible developed flow. So for this case, it is under developed flow. So this flow pass through the entrance length. So the velocity profile will never change throughout the flow. So for this case, this is valid to apply the particle or elemental approach. So remember that elemental approach, we take out a small portion of the particle or element, and we solve it, we integrate it in order to get the whole solution. Alright, so the first we need to analyze the question, derive expression, velocity distribution, and flow rate. So, the first step, we can apply the elemental approach since this is under developed flow. Right? Under developed flow. So, only developed flow we can apply the elemental approach. So, step number 1, apply elemental, right? Elemental approach. Since it is under developed flow. Okay. So for this case, let's take it out one element here. Alright, for example, this is the element. We take it out, this element. Okay, we take this out. This portion. Alright, basically at the bottom is at the mirror pipe. Alright. So from this case, we have the shear stress. The flow from left to the right, we have the shear stress, which is pointing to the left. Alright, and then we have the shear stress as well in this direction. Okay, as well as we have the pressure force. We have the force here. So let's put all these elements together, which is at the bottom we have the shear force tau 2 pi r dx. 2 pi r is actually the circumference of the circle. Multiply with the dx here, we will get the surface area. So actually tau multiplied with surface area is the shear force. So again here, alright, so here is here, and then here we can get the change of radius here. We can get tau, okay, plus d tau 2 pi r. Alright, remember our radius. We start from this one. This is our radius, right? So radius is the change of radius. Definitely we have the change of radius. This is radius 1. This is radius 2. So we have the change of radius. So that's why 2 pi r plus r plus dr multiply with dx. So this is actually the area, the surface area, and this is the change plus the tau. This is actually mu tau, tau number 2. This is tau number 1 multiply with 2 pi r dx. So in here we have the pressure force. Okay, we have the pressure force, which is P multiply with area 2. Okay, 2 pi r dr. Okay, and here P, alright, this is P number 2, P plus dP multiply with 2 pi r dr. Alright, this is the circumference multiply with radius. Alright, so from here, from the free body diagram here, by using the elemental approach, we can use the summation of force in x component equal to 0 because we consider this under steady flow. Alright, because this is under steady flow, we consider under steady flow. there is no accelerating component because this is already developed. The velocity profile will never change. That's why it is steady velocity. So steady velocity means the acceleration equal to 0, summation of force in the x component equal to 0. So this is the pressure force. Just include here P 2 pi r dr. Alright, this is going to the left minus P plus dP 2 pi r dr, and then this one going to the right is positive. Positive tau 2 pi r dx. Alright, and then here to the left is minus tau plus d tau, the change of tau in this location, multiply with 2 pi r, okay, multiply with r. 2 pi r, this one is actually 2 pi only, not r. Okay, so from here we can delete 2 pi only. Okay, so this is correct, 2 pi r. So from here, okay, this is r plus dr multiplied with dx. Okay, so from here equal to 0. You need to simplify further by expanding here. This one multiply with this one, multiply with this one. You will get P 2 pi r dr minus P. This one multiply with P 2 pi r dr. You have to multiply with this one. And then negative dP. This one multiply again with this one. 2 pi r dr plus tau 2 pi r dx. This one you have to solve. Then you multiply with this one. Okay, and this one multiply with this one, multiply with this one. Okay, so tau minus tau 2 pi r dx. This one tau multiply with 2 pi, multiply with r, multiply with dx. Okay. Okay, and then continue again. So negative d tau multiply with 2 pi multiply with r. Okay, we try to solve this one first. Okay. Alright, after we have multiplied with this one, okay, this one, and then you can solve this one, dt. This is dt. After that, you need to solve again with respect to dr. So negative tau 2 pi dr dx. Okay, and then again you need to apply negative d tau 2 pi dr dx equal to 0. Okay, so from this one you need to simplify. So this is the same, cancel out, and then this one tau 2 pi r dx cancel out, and then you try to find out, okay, dt 2 pi r. Okay, so from here there is nothing more, the same. So just write it down that you have simplified. Negative, okay, dp 2 pi r dr, and then this one negative d tau 2 pi r, and then this one negative tau 2 pi dr dx, and then this one, the last one, negative d tau 2 pi dr dx equal to 0. Alright, for this case, you need to divide the whole term here with negative 2 pi r dr dx. to simplify further. Alright, so you divide it here, the whole term, okay, with 2 pi, negative 2 pi, this one negative, 2 pi r, dr, dx. So this dr cancel, okay, and then 2 pi r cancel, only dp. So left, this is negative, negative cancel. So dp over width, this one, dp over width, left dx. Alright, so this one negative, negative cancel, positive. Alright, 2 pi r cancel. Okay, d tau, we have d tau. Okay, from here, okay, so we cancel out this one. Let's take a look on this. Okay, this one d tau. We have another one dx actually. So this should be dx. Alright, so dx cancel. Okay, so we have here d tau over width. This one cancel, only dr. Okay, this one negative cancel, 2 pi cancel, dr cancel, dx cancel. So we left tau over r. Okay, this one again, d tau, don't have here, dr cancel, dx cancel, 2 pi cancel, and this one positive. So positive, d tau over width r equal to 0. Alright, this is the final part where we simplify the above equation. So from here, you can arrange that you need to make the dp over dx equal to the other term. So change this one, negative tau over r, okay, negative d tau over dr, negative this one, d tau over r. So let's take a look. Is there any change of tau with the constant radius? So with the constant radius, there is no change in d tau. So this one is actually equal to 0. At constant r, d tau is actually equal to 0. Alright, there is no change in d tau. So from here, okay, we know that this is step number 1. Step number 2, we know that tau is actually negative mu du over dr. Right? So from here, negative means it is near outer wall. Alright? It is actually to give this value to become positive back. Okay, because this one, this is r. When it is near, normally near is actually refer to y. Alright, when we refer to r, should be negative r. So that's why negative go outside. So substitute into this equation. Okay, substitute back, where dp over dx equal to negative tau, just substitute mu du over dr over r minus, this is d, tau again, mu du over, this is negative, over dr over dr. Okay, and then you will find out that this is actually negative. Negative, negative, positive, mu over r, du over dr. This is positive. Okay. This one you try to do the differentiation. This is multiply inside. Mu d squared u over dr squared, because dr multiply with dr squared. So from here you need to factorize mu. Okay, you will get 1 over r du over dr plus d squared u over dr squared. Right. Okay. Remember that in this case, near the wall, okay, the value of du over dr is actually equal to 0, because near the wall, the velocity is 0. So this one, only the change of the velocity near the wall is equal to 0. We can cancel out this term, only leave. Okay. Alright. For this part, after you have factorized mu, okay, and then since we know that near the wall u is actually equal to 0, so the change of du over dr equal to 0. So this term we can cancel out. So mu d squared u over dr squared. After that, alright, try to rearrange like this. Mu over r. This one we separate d over dr. And then we factorize r. We do r multiply with r. We try to do the conjugate of r with r. And finally, this is du over dr. Alright. So after this step, this is step number 2. We need to integrate. So step number 3, integrate the solution. Alright. So after we have arranged this one, and then we need to integrate those solution here. You can see here. So how to do the integration? You need to rearrange back. So from here, alright, you can move r dr, dp over dx equal to mu d r du over dr. And again, you can move mu to the other side, become 1 over mu r dr dp over dx, right, equal to d r du over dr. So directly integrate both sides. This integration of differentiation cancel out, neutral. You will leave r du over dr equal to integrations of 1 over mu r dp over dx with respect to dr. So this is constant, move outside. So r du over dr equal to 1 over mu dp over dx integration of r dr. You integrate r, will get r squared over 2. So r du over dr equal to 1 over mu dp over dx r squared over 2 plus a. This is constant because the integration has no limit. Since it is no limit, we have to plus a. Alright, when the integration has limit, we don't have to plus constant. So from here, we need to move to do another integration because we have the change of dr over du over dr. So we need to move r dr to the other side as well, and then we do the integration again. So this is step number 3. We go to step number 4. Move this one with that du equal to, alright, write it down, 1 over this one, mu multiply with 2 mu. We try to simplify dp over dx r squared multiply with, this is r we go to the other side, dr over r plus a multiply with dr over r, because this is coming from this one. You can see here, dr over r. So you try to simplify again, 1 over 2 mu dp over dx. This is r, we r cancel out, r dr plus a 1 over r dr. So integrate both sides, integrate. We can get finally dA is constant, move outside. This one is actually constant, move outside. So this integration will leave u with respect to r. So we do integration. Okay, r we get 1 over 2 mu dp over dx. This is r squared over 2 plus a. The integration of 1 over r will get ln r plus b. Because this is no limit integration, we have to plus constant b. So after this step, we need to find the value of a and b. Alright. So this is step number 5. Number 5, where a and b are arbitrary. Alright. So they are found by setting u equal to 0 when r equal to r1 at the pipe wall and r equal to r2 both. Right, you can see here from the definition. Okay, when r equal to 1, u equal to 0. When r equal to 2, u equal to 0 as well. So we have two conditions in order to get the a and b. Okay, find a and b through condition. Okay, condition of u equal to 0 when r equal to r1 and u equal to 0 when r equal to r2. Alright, so just substitute here from this one, u equal to 0. Okay, 0 equal to this one, 2 multiply with 2, 4, 1 over 4 mu dp over dx. This is r, become r 1 squared plus a ln r1 plus b. This is equation 1. Okay, using this condition. Another one using another condition, 0 equal to 1 over 4 mu dp over dx. This is r2 squared plus a ln r2 plus b. So you try to solve subsequently, simultaneously for 1 and 2. Finally, you will get a is equal to 1 over 4 mu dp over dx r1 minus r2 squared and squared over with ln r2 over r1. Alright, this is a. However, for the b equal to negative a ln r2 minus r squared 2 over 4 mu dp over dx. This is by solving a and equation 1 and 2. Thus, our u of r is actually equal to 1 over 4 mu dp over dx. Substitute the value of a and b. Finally, you will get r squared 1 minus r squared of 2 plus r2 squared minus r1 squared over ln r1 over r2 ln r over r2. Alright, this one is actually r only. R squared minus r2 squared plus r2 squared minus r1 squared. So this is the velocity distribution or velocity profile with respect to r. So in order to get the value of volume flow rate, okay, we need to do the further integration. So this is step number 5. Step number 6. Okay, integrations of volume flow rate. We need to do the integration. So Q is actually equal to, okay, R1 to R2 U with respect to R 2 pi R dr. This is actually, okay, this is velocity, this is actually area. Remember, Q equal to A multiplied with V. So velocity from profile R1 to R2 multiplied with the area. So this is the area where the area of the circle, basically area of the circle is pi R squared. Alright, this is the cross-sectional area dA. So this is the, we differentiate A, dA, 2 move front, 2 pi R become dr. So we take this out to replace this term. Okay. And then you try to do integration with respect to R1 to R2. So UR, you find out to be this one, 1 over 4. Just substitute the whole equation back. Okay, 1 over 4 mu dp over dx integration bracket r squared minus r squared 2 plus r squared 2 minus r 1 squared over ln R1 over R2 ln R over R2. Okay, and then this one, okay, you have to add 2 pi R dr. Okay, and finally you do the integration, you will get negative pi over 8 mu dp over dx, right? Integrate bracket r power of 4 squared, r2 the power of 4 minus r1 the power of 4 minus r2 minus r1 squared the power of 2 over ln r2, alright, r2 over R1. Therefore, that is the final answer to get the volume flow rate distribution as well as velocity profile.